In these questions, you are given a 7-segment LED and then you're asked to implement or design a combinational logic circuit to implement or to control this 7-segment LED. So this is a circuit that is given. So the LED circuit, you see that is driven by a high logic through an LED to ground. Okay, so the A, which is pin here A, need to have a high logic in order to drive or to turn on the LED. And the pin A is control the LED lights here on the top. Pin B is on the vertical lines here B, or the vertical LED, and so forth. So in this question, you're asked to design the circuits to control pin A and pin B only. So you're not asked to design the whole system, but just for pin A and B. So the first one is to design this using basic gates. So to do this, we first list down all our possibility. And you also said that the input of this is a BCD code. So we have A, B, C, D, and list down all the possibility. So for A, we go through our list of our BCD code. So we go from 0, 0, 0, which is 0. So we need for 0, so this is the display of the LED or the 7-segment LED. So we need A to be on and B to be on. So we need 1 and 1. And for the number 1, A is off, B is on. So we need 0, 1, 2, both is on, 3, both is on, 4, A is off, B is on, 5, A is on, B is off, 6, A is on, B is off, 7, both is on, 8, both is on, and then 9, both is on. And our BCD code doesn't have 10, 11, 12, 13, 14, and 15. So in this case, we don't care what the output is. Because we don't have this inputs. So next we want to transfer this into the CAR map so that we can minimize the function and build the logic circuits. For function A, so A, B, C, D, so go from 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So for A, let's go from 1, 0, 1, 1, 0, 1, 1, 1. Then 1, 1, X, X. I go X, 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 X. So we can minimize our function by drawing loops. So here is a loop of 8. So F is equals to, so here we have B changes, C and D changes all throughout. So we have A plus, here we can draw another loop of 8. In this case here A and B changes, and then C is the one that stays the same. Here we can draw a loop of 4. Here we can see B stay the same and D stay the same. So we have B, D. And then here we can draw another loop of 4. In this case now B bar is not changing and D bar is not changing. So we can build this circuit using our basic gate. So here we have A and C is an OR gate. Here we have an exclusive NOR. Let's go to our pin A. Then we can do the same for our function b. So we have 1, 1, 1, 1. Then we have 1, 0, 0, 1. Then we have 1, 1, x, x. Therefore x here. So again we have a loop of 8 here. Function f. Should be function b. This should be function a. A plus then we have a loop of 8. This will be b bar. Then we have a loop of 4 here. There will be c bar, d bar. Another loop of 4 here. This will be cd. So we have our a, and then b inverted. And we have CD exclusive NOR gate, and then O, and this go to our pin B of our 7-segment LED. Okay, so that is the solution for part A. For part B, you're asked to design the combinational logic circuit using a 4-bit active low decoder. So if I look at the truth table at the function A, so for active low, we can write down, so we need the max term of 1 and 4, so just 1 and 4. So our functions A the product of sum of 1 and 4, which is our max term m1 and 4. And for function b, there will be 5 and 6. Or m5, m6. And the question specified that you need to design this using 2 inputs universal gate. So meaning that you can either use NAND gate or NOR gate. So it's an AND function, so a NAND gate probably will be the easiest to implement. So we need M1 and M4. Put this through our NAND gate and then invert it. So we are A, M6, M5, to be B. For part 3, you're asked to design it using an active high decoder and also using 2 inputs universal gate. So active high, so the output here is the min terms. So if we write it as the products, the sum of products, that will be in the min terms. So A will be equals to so we have 0, 2, 3, 5, 6, 7, 8, 9. Zero, 2, 3, 5, 6, 7, 8, 9. And B is 0, 1, 2, 3, 4, then 7, 8, 9. Zero, 1, 2, 3, 4, 7, 8, 9. So you can see that here, our A and B terms, there's a lot of min terms here. So if you're going to all of them together, you're going to use a lot of logic gate. So maybe it's still a good idea to implement it using the max term, or we can look at how we can simplify this. So if we do a De Morgan's, so that will be back to our so this is meant to be sum of products. So if you do a De Morgan's, that would be product of sum. Back to what we have previously, 1, 4. So this is our max term, M1, M4. If we double inverse this, we're going to have M1, apply De Morgan's, M4. But we know that our min terms M1 is equals to our max term inverse. Therefore, our A is equals to our min terms plus min term 1 plus min terms 4, then bar. So meaning that we can implement our A, taking 1, which is our min term 1, and then min term 4, put it to our NOR gate. That will be my A. And then B, again, if you do De Morgan's, there will be 5, 6. There will be M5, max term 5, max term 6. Again, double inverse this, apply De Morgan's. We have M5 plus M6 bar. This is equals to min terms 5 plus min terms 6. This will be B. So it's a lot simpler comparing if we're going to use these functions here. So if you use these functions, then you're going to use a lot of gate to implement this. So next question. So we're going to repeat the same questions, but previously for all the invalid code, we don't care about it. But in this example, if it's an invalid BCD code, we want to display the letter E. And the letter E in 7 segments show up like this. So again, go back to our truth table. You can write down A, B, C, D. So the first 10 is the same. Zero to 9. So 4 is 0, 1. And here is 1, 1. And then the rest 10 to 15, we want to display E. E will be 1, 0, 1, 0, 1, instead of done K. Now we're going to put this into the K-map again. So A, we have 1, 0, 1, 0. Sorry, 1, 0, 1, 1. Zero, 1, 1, 1. Then we have 1, 1, 1, 1, 1, 1, 1, 1. So here we have a loop of 8. Then here is another loop of 8. And here is loop of 4. Here is a loop of 4. So it's exactly the same as the previous one. So no different from the previous example. For B, one, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, and then the rest are all 0. So here we have a loop of 4. Which is A bar, B bar. Another loop of 4 here. That will be B bar, C bar. Then we have a loop of 2 here. That will be A bar, C bar, D bar, plus loop of 2 here. That will be A bar, C, D. We can factorize this. So we have A inverted, B inverted, C inverted. So A, O with C bar, A bar, O with C bar, and then N with B, then O will be our B function. Then part 2. Part 2 is to implement this using active high decoder. So you can see that for function A, stay the same compared to the previous one. So the previous one, all the x we make it into 1. So in this case here, for the function A, there's no change. So we don't need to redo that. So we're going to just look at function B. So active high, so there will be in mean terms. So if you can write down function B as the mean terms, sum of products of 0, 1, 2, 3, 4, 7, 8, 9. I'm going to implement this using an active high decoder. So A hasn't changed. To implement B, so we have 0 and 1. Then 2 and 3. Four and 7. the 8 and 9. That will be our B function. And then part 3 using active low decoder. Again, A stay the same, B can write down B, product of sum, 5, 6, 10, 11, 12, 13, 14, 15. Okay, so we have 5, 6, 10, 11, 12, 13, 14, 15. Even if we manipulate this to using the sum of products, it's not going to make much difference, or we're not going to make any saving in terms of the gauge, because there's almost equal amount of terms, whether it's in the sum of products or product of sum. Okay, you can write that down. If you want to write this in sum of products, there will be 0, 1, 2, 3, 4, 7, 8, 9. So we have 2, 4, 6, 8 terms here. Then we have 2, 4, 6, 8 terms here. Okay, so whichever way you want to manipulate it, they will end up with the same thing. So in product of sum, we can write B as M5, M6, M10, M11, M12, M13, M14, M15. So to implement this, so we have M6, M5, M6. So we can end this too. Put this through to a NAND gate and then invert it. Then M10, M11, 12, 13. $14, 15. Then we can end this. There will be B. For A, it's the same. Haven't changed. B. So that's the solutions for these questions.